What's up guys, this is Massey. Welcome to another video. In this video I want to talk about precipitation conditions and solubility and KSP and things like that. I have two questions in this video. The first one is saying what mass of ZnS, zinc sulfide, KSP 2.5 times 10 to the power of negative 12 will 10 to the power of negative 22 will dissolve in 300 milliliter of 0.005 molar of zinc nitrate. So ZnS, zinc sulfate, is solid. When it dissolves, it's going to produce its ions like that. Actually, this. And here we have aqueous solution. In aqueous solution, we need to have the I stable. We don't write anything for initial and equilibrium for solid phases. What about this side for the ions? Do we have any of them? So obviously there is no sulfide initially in the solution, but since we are finding the solubility in 0.005 molar zinc nitrate solution, it means that we initially have some zinc ions, which is 0.005. Then change is going to be negative x plus x plus x. Equilibrium is going to be 0.005 plus x, and here is going to be x. So KSP equals to 2.5 times 10 to the power of negative 22 equals to 0.005 plus x to the power of 1 times x. So now what we can do, I can neglect x comparing to 0.005, because if we assume 0.005 is much greater than x, we can assume that 0.005 plus x is approximately equals to 0.005. So it's going to be 2.5 times 10 to the power of negative 22 equals to 0.005 times x. So x will be divided by 0.005. That's going to be 5 times 10 to the power of negative 20. So that's the solubility. It means that the assumptions we had in here was valid. So now this is molar solubility, so it's mole per liter. The question is saying what mass of ZnS will dissolve in 300 milliliter. So it's going to be mass of ZnS that dissolves. We have 0.3 liter or 300 milliliter times 5 times 10 to the power of negative 20 mole ZnS divided by liter times the molar mass of ZnS is 97.45 grams ZnS mole equals to 0.3 times 5 times 10 to the power of negative 20 and 97.45. That's going to be 1.46 times 10 to the power of negative 8 grams. So 1.46 times 10 to the power of negative 18 grams is going to be the mass that is going to be dissolved in 300 milliliter of 0.005 molar of zinc nitrate. Let's see another example. In this example, it says that the concentration of magnesium ion in seawater is 0.052 molar. At what pH will 99% of the magnesium ion be precipitated as the hydroxide salt? KSP for magnesium hydroxide is 8.9 times 10 to the power of negative 12. So the salt we have is MgOH2. In solid form, when it dissolves, it's going to be Mg2 plus 2 OH minus, both in aqueous phase. Initial change equilibrium, exactly like the previous example. We don't write anything for initial and equilibrium for solid. Initially, do we have magnesium and hydroxide? Definitely we don't have magnesium before dissolving. But hydroxide is 10 to the power of negative 7. At pH equals to 7. But at different pH values, we're going to have different concentration of hydroxide. The question is asking at what pH will 99% of Mg will be precipitated. So KSP is going to be Mg2 plus times OH minus to the power of 2. We need to find out the concentration of OH, and based on that we can find out the pH. So what should we have KSP? So what should we write for Mg? It says 99% of Mg has to be precipitated. It means that only 1% of it is going to remain dissolved. So Mg concentration is going to be only 1% of 0.052. Because as you remember, it says the concentration of Mg in seawater is 0.052. 1% of it is going to be 0.01 times 0.052, 5.2 times 10 to the power of negative 4 mole per liter. KSP is 8.9 times 10 to the power of negative 12, 5.2 times 10 to the power of negative 4. OH to the power of 2 will be 8.9 times 10 to the power of negative 12 divided by 5.2 times 10 to the power of negative 4. That's gonna be 1.711 times 10 to the power of negative 8. So OH concentration will be 1.3 times 10 to the power of negative 4 molar. So now based on that we can find POH and pH. So POH is going to be negative log of OH concentration. That will be 3.89. So pH will be 14 minus 3.89, which is going to be 10.12, or let's round it to 10.1. So at pH 10.1, 99% of Mg in seawater will be removed as magnesium hydroxide. This is the final answer. I hope you enjoyed this video. Please leave me a comment if you have any question. Please don't forget to subscribe this channel. You can have access to many other videos regarding solubility and other topics in chemistry, physics, and math. Thank you for watching and have a great day.